Oh wow, I am so excited to be here with you to talk about applied optimization. We're in section 4.7. This is the ultimate section for our use of derivatives. And wow, is this a great chapter? I've got a couple of YouTube videos about this content, which in some ways may resemble that from the related rates and that they're word problems. And so the first one is advice, which is kind of what we're going to start with after we go through a quick refresh, and then a completely worked demonstration problem that we'll talk about a little bit in this lecture, but not a whole lot. So if you want an additional work example, go ahead and check that one out. That one's pretty cool. It's also discussed in our textbook, which I do deliberately so that you can get another person's perspective on the same thing by visiting both my notes. Sometimes I do the same thing in my Lightboard videos, and then our textbook author as well. And that's deliberate. That is not a mistake. I do think that reading the textbook is a useful thing to do. So let's do a quick refresh on optimization techniques. We found 3 techniques in the course of chapter 4 so far. We did global or absolute optimization. That was in section 4.2. We did local optimization using the first derivative test. That was in section 4.3. And then we learned the second derivative test in 4.4. In general, in the content that we're doing right now, we're just interested in the maximum or minimum, and so we'll tend to be in the world of global optimization, finding the absolute optima, as opposed to the local optimization for these types of problems. Of course, we can always state things a little bit differently, and we can need local optimization. So you can't be ignorant of sections 4.3 and 4.4, but generally we're going to rely on section 4.2 global optimization as we do these problems. What makes this section 4.7 so novel is that we will come up with the function to optimize. We're going to call it the objective function because our objective is to optimize it, right? The objective function. I really like calling my objective function omega because omega stands out. Like, we have not used omega, and that's a pretty mediocre omega. We have not used the symbol omega anywhere so far in this class, and so it really stands out. Plus, like that is just a fun character to draw. Like go ahead and draw some of that. That is just like, boop. Oh, that one was pretty good. A little imbalanced. Yeah. Okay. Anyways. What a great character. It's a capital O in Greek. So, as a preview, I will make the full disclaimer right up front. There is an infinite number of problems we can come up with. And the main challenge in these, just like with related rates problems, the main challenge is often determining the objective function. After that, it's just an optimization problem. And so how do you get good at coming up with the objective function? It's not procedural. That's the creative part. That's where you're gonna like draw pictures and use geometry and stuff like that. So I have a first example on the screen right now. A piece of wire is bent into a rectangle. What dimensions produce the rectangle of maximum area? That's a fully stated applied optimization problem, and a rather simple one too. In fact, it's the first example that's given in our textbook in this section. And so what you've got to be able to read out of this is the setup of the problem. You got to be able to come up with the objective function and then figure out what do you do with it. So I think that our objective function is going to come from an area. It's going to be an area function. So like omega is going to equal area of, and then I need to figure out what my variables are. Right? So we got to come up with those. What dimensions? Okay, that's suggesting maybe we've got like x and y, or like w and h, or something like that. Right? And then maximum. Right? So in this particular problem, we're going to maximize area. And we're going to come up with area as a function, and that's going to be our objective. So let's turn the page. Here's another typical problem. All units in a 30-unit apartment complex are rented out when the rent is $2,000 a month. I'm glad I do not live there. A survey reveals that for every $100 increase in rent, demand decreases, and one additional unit will sit vacant. Suppose that each unit occupied costs $200 a month in maintenance. Which rent maximizes profit? So to me, it kind of screams out, okay, rent is going to be my objective function. Rent is omega, and we're going to maximize omega. Here's the cylindrical can problem. Design a cylindrical can of volume 900 cubic centimeters so that it uses the least amount of metal. That is to say, minimize the surface area of the can. I think that it was well stated, even without this. This was a hint. The least amount of metal. So the metal is proportional. Metal is proportional to surface area. So we are minimizing omega equals the surface area, right? And we have to come up with what the variables are, like it's up to us. Find two positive real numbers such that they sum to 108. And the product of the first times the square of the second is a maximum. This one, I like this problem. This problem's good. This family of problems is really awesome. Right? So there's a constraint. This number sum to 108. That's going to be a relationship. So that I can go from one variable, or two variables to one. Because we only know how to do one variable optimization in this class. And then I've got the product of the first times the square of the second. The product of the first times the square of the second. That's omega maximum. Maximize omega equals, x times y squared. A flexible tube of length 4 meters is bent into an L shape. Where should the bend be made to minimize the distance between the two ends? L, ends, distance. All right. Where? Minimize omega equals distance. All of these problems are novel. I cannot show you how to do all of them. The best way to get used to this is to just practice and be creative and talk with people as you struggle in doing them so that you can build the intuition to understand the types of geometric things that we tend to do in these problems. Let's turn the page. So I want to do some tactics, advice, and give you a procedure. Knowing that my students, in my experience, often are most interested in how do I do this? And struggle with these types of problems just like they do with related rates because I can't tell you how to do them because there is no general procedure. They require thought and creativity. You got to name the variables yourself. You're the one who's got to come up with that constraint equation. You're the one who's got to come up with that objective function. I can't do it for you. I can't tell you how to do it. You have to learn how to do it. It really is artistic. These problems require thought and creativity, but they're good practices. The book recommends a general 3-step process. Choose variables, find an objective function, and possibly an interval if there is one. And then 3, finally, optimize the objective function. My procedure is a bit finer in terms of steps. I suggest these 6 steps to you. Step 0. Be willing to think. Be willing to be frustrated and be willing to start over. And then, if you allow yourself to do that, you have the freedom to do the following. First, I think you should draw a picture. Second, I think you should choose variables and label everything in the picture. Third, I think you should try to find your objective function and write it down. Omega equals, right? Omega of your variables. Identify the interval if in fact there is one. 5, we should optimize the objective function. That's like f prime equals 0, solve. And then finally we should conclude, because it's really easy to end our solution prematurely and not give back what was really asked for, but to accidentally give them what they didn't ask for. So I think referring back to the original problem is critical in terms of doing this process. So I think that we should solve some problems. Again, I can't solve every type of problem for you. I cannot possibly model solutions for everything that I can possibly think of in terms of these applied optimization problems. But there are patterns, and by doing lots of problems, you'll see the patterns. And it's not by me doing lots of problems that you'll see the patterns and really internalize them. It's by doing it yourself. So it is not a valid complaint. We didn't cover this type of problem in class. That is not a valid complaint. That is not a valid reason to not understand a problem. Though it is a good reason to come and talk about it in office hours or in our class discussion. A piece of wire is bent into a rectangle. What dimensions produce the rectangle of maximum area? You better believe I am going to draw a picture. Rectangle. What dimensions produce the rectangle of maximum area? A piece of wire. Oh, okay. So I think I need to say that the wire starts and stops here. That's what I'm going to do for my rectangle. The total length of this wire, let's call that L for length. The total length L is also equal to 2x plus 2y. And the reason that I need that is because we're going to be doing the maximum area, omega equals area, and that's the product of x times y, right? So I've got x times y. I've got my objective function, but it has multiple variables. Multivars. That really did say multivars, right? X and y, you got to get rid of one of those. And you might be like, oh, but then I get L. And it's like, okay, but that's fine because L is constant. And we're just looking at what the dimensions are. The solution of this problem is very cool. It's kind of prototypical. So let's solve for y, because that feels a bit like and let's write like L equals L minus 2x equals 2y, which means that y equals L minus 2x over 2 equals L over 2 minus x. Alrighty. What I want you to here's a cool note for you. Note. Area equals 0 if x equals 0 or if x equals L over 2. X equals 0 would mean that I would have this stupid one, right? Because then x would be 0. So I would have this rectangle, which has no area. And otherwise, if x is L over 2, then half of the length is used up in each of those. Y is 0. And my rectangle is this stupid rectangle with no interior. I like doing those sorts of sanity checks. And I think that the people who do the sanity check are probably going to be the most successful in this. All right. So what's my objective? Oh my God. Okay. So like, I feel like I kind of like wandered away and like, now what am I doing? I'm deliberately doing this because I want you to ask yourself that question. What are you doing? What are we doing? I am maximizing area. Omega. We're maximizing area. Okay? Maximize area. Well, let's see here. So I've got a domain of validity. And that kind of relates to this discussion we had about when area equals 0. I can't have negative area, right? So x lies in between 0 and L over 2. Because if x lies outside of that, then I get negative area. All right. So I've got area, so I'm going to take area prime. Let's call it omega prime. That's equal to L over 2 minus x plus x times minus 1. I use the product rule on the area function. Right, I've got this product here. Now we'll simplify, and I want to find the critical points. L over 2 minus x, 0 equals L over 2 minus 2x, which means that 2x equals L over 2, which means that x equals L over 4. Oh, that is just, here comes the highlighter. I'm going to use a highlighter. Yeah, x equals L over 4. That is so cool. And we should note that there was one critical point, and that my area function is negative. So I've got my function, and 0 to L over 2, this is where x lives. F is less than 0, f is less than 0, f is bigger than 0. And my critical point that I found is right here, L over 4. Which means that my function looks like this. Because it's differentiable. I mean, it's a parabola. It's a downward opening parabola. So we just verified that we do in fact have a max at L over 4, which is kind of an important little step. I could have also used the first or second derivative tests, but I decided to reason about it that way. Math is all about the reasoning. So I found my solution, L over 4, and so we haven't concluded yet, right? So the question is, what are the dimensions? So the dimensions, are of the rectangle are L over 4 by L over 4, that is to say, a square. It's not that rare that something neat comes out as a solution of one of these problems. Let's turn the page. Ooh, I like this one here. All units in a 30-unit apartment complex are rented out when the rent is $2,000 a month. Okay, so let's call it R for the number of units. No, I think that's a mistake. I think the number of units should be X, because I also saw that there's this rent There we go. I just started naming things. I'm having a hard time drawing a diagram. What is my objective? Which rent maximizes profit? Omega equals rent. Rent equals rent is a function of, no, rent is not a function of X. Rent is set by me. Omega is rent. Oh. Let's see here. Okay, well, let's just start writing down some stuff. Let's see what the rent is. Is a function that's going to be, no. I know what my problem is here. It's because I said omega is rent, but omega is profit. It's screaming that to me right here. Profit. Which rent maximizes profit? Ooh, I'm maximizing profit as a function of rent. Okay. Again, I deliberately reason about these things and don't thoroughly prepare because I don't want to do them perfectly, because there's so much value in you experiencing my thought process as I make mistakes. My mistakes are just as valuable as what I do correctly. So profit is a function of rent. I named my rent R. Omega equals omega of R. Profit is equal to number of units times the rent per unit is X times R. Ooh, it's not just number of units, it's number of units rented out, right? X is the number of units rented out. I know that, and that's a function of the rent. I know that X is a function of the rent because I see that all units are rented out when the rent is $2,000 a month, and that when I increase rent, one additional unit will sit vacant. So X of 2,000 equals 30. And I know that X of 2,100 equals 29. X of 2,200 equals 28. X of 2,300 equals 27. Right? Do you see? This is a line. I think just writing down those things right there kind of like really helps me get a handle on what's going on as far as the rent and the number of units. When the rent is 2,000, the number of units is 30. And as the rent increases, the number of units rented out decreases. So I kind of like, when the rent is 2,000, the number of units is 30. When the rent is 2,100, the number of units is 29. I have a triangle right here, and we need the slope of that triangle. So what's the rise? Is -1, and the run is 100. So the slope of this line is -1 over 100. It goes down 1 unit for every 100 the rent increases. All right, I've got a slope. I also happen to know a point on the line. That point is 2,030. So let's use point slope form to write x equals x of r. X minus x naught equals m times r minus r naught. Now you might rebel a bit at the naming of the number of units being x, because now we're thinking about x as being an output here, and r is the input. So x is the dependent variable, and r is the independent. And if your mind is rebelling with that, you could always go u for units, right? Because variable names are arbitrary, and I really don't, it doesn't matter. It'll have no impact on the solution. And so let's just make that switch to u, because I feel like maybe that will help improve things here. Are you okay with that? I guess it doesn't matter whether you're okay with it, because this is a recording, and I'm going to commit. Okay, so I think the point of me leaving this decision in and me having changed my mind just now is that sometimes the variable names that you start with are not the variable names that you end with, and that, going back to my advice, step 0 is be willing to think, be frustrated, and start over, right? Like, you have to be willing to make mistakes. You have to be willing to change your mind about things, because if you latch on, then you're never going to be effective at solving these problems. So, I think we're really close now to having my units rented out as a function of rent. And what that's going to do for me is it's going to let me have my profit function as a profit purely as a function of the rent that I set. So, u minus 30 equals minus 1 over 100 times r minus 2,000. U equals minus 1 over 100 times r minus plus, because I've got double minus signs, so plus 20. Plus 30. U equals minus 1 over 100, r plus 50. I do believe that I'm correct. Let's do a quick little checksum on that 50 right here. So if I were to go this direction, that would be how many steps of 100? So every step I go up 1. Every step left I go up 1. That would be how many steps of 100? 20 steps, and then I'm going to go up 20. Okay, and then 20 plus 30 is 50, which is my 50 that I see right here. Okay, cool. So I have faith in that 50. What does that give me? Going back to my profit. Profit is the number of units times the rent per unit, U times R. We just found that U equals minus 1 over 100 times R plus 50. Right? So now I have profit as a function of the rent. Right? Well, that's good, because I wanted omega equals omega of R, because which rent maximizes profit. So my fundamental independent variable is the rent. So I think we're ready now to take this expression with this substitution and go down here and write down what omega is. Omega equals omega of R equals u of r times r is equal to minus 1 over 100 r plus 50 times r. This is a downward opening parabola. I know that because I've got a leading one here, and I've got these two r's here. So this is going to look like minus something times r squared plus other stuff. And it's this term right here that leads me to have the downward opening parabola. So I've got a downward opening parabola. As far as the profit function, omega, the profit function, equals 0 if r equals 0, because then I'm not charging anybody. Or omega equals 0 if r equals 5,000 because no one rented. Because I charged too much. Right? If you plug in 5,000 to that expression, you get 0, and you'd have 0 times something, and you get 0. So, we get a parabola, and the optimum is going to happen between its two roots. The solution to this is going to be 2,500. Let's find out, using the methods of optimization, whether I'm right or not. Omega equals minus 1 over 100 r plus 50 times r. Omega prime, because we need to find the critical points, omega prime is equal to minus 1 over 100 times r plus minus 1 over 100 r plus 50 times 1. I just did the product rule on that product right there. R went to 1, that thing went there. I want to find the roots of this thing. 0 equals minus r over 100 plus minus 1 over 100, ooh, that's an r, plus 50. 0 equals minus 2r over 100 plus 50. Let's move that 2r over 100. Plus 2r over 100 equals 50. Let's multiply by 100. And then I'll have 2r equals 5,000. And finally, r equals 2,500. Boop. Yeah, that's what I want. I want that. The rent is 2,500. What rent maximizes profit? $2,500. Calculus is powerful. This is seriously the tip of the iceberg. If you think that this is pedantic, if you think that this is trivial, if you think that this is pointless and not actually useful, you are dead wrong. So many products, so many engineering decisions, so many government decisions are made through processes like this, the process of optimization. This is incredibly useful. I think I have one more problem planned for you, and then I'll remind you that I have the surface area of the can assigned, or not assigned. I'm demonstrating and solved on YouTube, but I really like this problem. This family of problems is so cool, and in my experience, students tend to do really well on this one, and so I wanted to show you how to do it. Because once you get this one, hopefully you get a whole family of these problems that are all pretty easy, honestly. So let's take a look at this problem. Find two positive real numbers such that they sum to 108 and the product of the first times the square of the second is a maximum. Let's name things. The very first thing that I do when I get an animal from the shelter to adopt it, but to keep me company, is I name it. Two positive real numbers. What would you name them? A and B? X and Y? H and K? Alpha and beta? We haven't used alpha and beta in a while, and I think that they're really cool characters. So I'm going to do alpha and beta. That's the eraser. Ooh, let's constrain them. They sum to 108. What are we doing? Maximizing this weird thing right here. The product of the first times the square of the second. Alpha times beta squared. Omega. Maximize. We have two variables. Isn't that annoying? Let's eliminate one, shall we? And I vote we eliminate alpha because otherwise I'll have to substitute into beta and then deal with beta squared. Right? So I can solve for beta and then put it in here, but then I have to deal with the squared, and I think that's just going to suck. So both will lead you to the right place. I just don't want to do that. So from alpha plus beta equals 108. That's an 8. I get that alpha equals 108 minus beta. So I'll substitute it in. Omega equals 108 minus beta times beta squared. This is a cube. It's a cubic, and it looks like that. Why does it look like that? Because I have this minus right here. So the leading coefficient is less than 0, so it looks like that. If it was bigger than 0, it would go like that. Note that omega of 0 equals 0. Omega of 108 equals 0. That means that we can expect our maximum to be somewhere in there. Should we conjecture that it's 54? I think we should conjecture it's 54. So, damn it. Oh, I wish I were an Oscar. I don't know why I started saying that. Okay, our objective function is omega. That's 108 minus beta times beta squared. Omega prime, because I know that the max occurs at a critical point. And the critical points are determined by where the derivative is 0 in this case. Omega prime is minus beta times beta, is minus 1 times beta squared plus 108 minus beta times 2 beta. Again, I did the product rule. If you don't like doing the product rule on these problems, by all means, distribute this thing out and then just use the power rule. You'll get the same thing as me. We're doing the same work. I don't know which one is better. I'm going to find the critical points. That's where 0 equals minus beta squared plus 108 minus 2 beta squared. Ooh, I think, well, we'll see what happens with that conjecture. I think we're going to be wrong. I like being wrong. Being wrong is good. Anyways, 0 equals minus 3 beta squared plus 108. 108 equals 3 beta squared. 108 divided by 3. Oh my god, what is 108 divided by 3? What is 108 divided by 3? I kind of feel like I did something wrong. Yes. Do you see my error? I did something wrong. I failed to distribute. I failed to distribute. So I've got this 2 here, and I put it on that one, but I didn't go over there. Yeah, okay. I gotta go back and correct some stuff. Right? You gotta be willing to make mistakes. I value my mistakes. My mistakes are one of the things that really, really teach me. All right, I still believe that one. But the next one is going to be plus 108 is 216. There we go. Minus 2 beta squared. And 216 over 3. It's not a wonderful number here, but that's okay. So 216 divided by 3. Ooh, that's 72. So beta is plus or minus root 72. But I know that it needs to be a positive number because it told me so. So I'm going to discard the minus branch. All right. Root 72. Yeah, I was pretty wrong. I feel like I'm still making a mistake here. I really do feel like I'm making a mistake here. But that's okay. If I did make a mistake, then that's okay. Because someone in the class will find it and I will reward them with bonus points. Anyways, okay, so if that's what beta is, then alpha equals 108 minus root 72. Boop. And I am out of effort to find out what that number actually is. Yep. I could simplify root 72 if you want. You know, it could be like root 72 is square root of like we'll see here, 9 times 8, which is 3 times, I gotta turn that feature off. 3 times 2 times root 2. 6 root 2. 36, yeah, that checks out. I really thought it was going to be bigger than that. Anyways, I'm going to let it ride. If you find an error in this, I'll give, first one to find it gets bonus points as usual. I'll give double bonus points if I made an error in this. Anyways, I think that's all I have for today. Thank you very much. I appreciate your time. Bye, everyone.